Every day, the future's getting closer.
Welcome to Master the NEC, where we talk about the National Electrical Code and all things electrically related. My name is Paul Abernathy, your host, and welcome to today's podcast. Well, hello, everybody. Welcome to another episode of Master the NEC, where we talk about the National Electrical Code and all things electrically related. My name is Paul Abernathy, your host, and welcome to today's podcast. Today's podcast, we're going to talk standard method load calculations for one-family dwellings, but we're also going to correlate it how it applies to individual dwelling units when you're dealing with a multifamily building, for example. So this is what you're going to apply if you're dealing with a one-family dwelling, a two-family dwelling, say a duplex, or if you're dealing with three or more in a multifamily building. When you're calculating the individual dwelling unit, then we're going to talk about that method that's used today. And the reason we're doing this today, and we've done other podcasts and videos on the standard method, but there seems to sometimes be some confusion with how we roll through the process. And so it never hurts to give another one in order for people to really understand how these apply and what code sections you have to deal with. And so that's what we're going to do in today's episode. I also want to give a shout out to a sponsor of this episode, and that is going to be the Harris, Reed, and Seifert Insurance Group. Now, they have offices in Houston, Texas, and in Jupiter, Florida. The president of that company, which her name is Brittany Reed, truly helped me out in a real tough situation for our son's insurance. And I want to give a shout out to Brittany and thank their group for working through some issues that we had with the previous insurance provider that simply didn't want to follow some of the rules that are required by law. And anyway, they stepped in and kind of worked with us and got what we needed. So I want to give a shout out. Anybody out there that's looking for insurance, definitely check them out. I will have a link to their insurance group down in the description. If you're in Texas, Florida, Michigan, Georgia, South Carolina, or even Virginia, then this is a great group if you're looking for insurance, whether it's your home, your car, or business, or marine, or even some specialty stuff. Give them a call. Their number is 561-768-8276 or 713-487-5538. And again, I highly recommend them. They really worked with me in helping my son out. So I really appreciate Brittany and her staff for helping us out. Even late into the evening, they worked with us. And so I appreciate them. And again, all of our listeners out there, you're looking for insurance, give them an opportunity. Tell them that Paul sent you. And again, I'll give a link to their website down in the description below. All right, today we are going to talk load calcs. And we want to make sure that everybody understands load calculations for the one-family dwelling. Why? Most exams are going to be based on a standard method. In the real world, we're probably going to use an optional method because it's usually always going to result in a smaller service. And again, if we can be smaller, that means we don't have to pay for larger wire, we don't have to pay for larger equipment, and based on diversity, it comes out okay. I mean, we're not going to have a problem. And historically, it's not been an issue. In fact, for the last 30 years, most of my calculations have always been based on the optional method. It's always going to result in a smaller. Now, can I use the standard method? Absolutely. That is absolutely available to you. And also remember, even if we do an optional method, we still got to know how to do the standard method because when we're sizing for the neutral or grounded conductor, we have to use the standard method as the formation of how we come up with that load for the neutral. Okay? We can't do that from the optional. We have to use the standard. So, if I teach you how to do the standard and you know how to do the optional, you're still going to have to know how to do the standard if you're going to do for the neutral. And we'll have a separate podcast dealing with sizing the neutral load calculations to the one-family dwelling and even the multifamily. So I'm going to break these down into multiple podcasts to make it really easy for people to listen and not have to listen to over an hour. Now, I don't know how long this one will take, so I'm not offering any apologies up front because you all know I'm very long-winded, but we're going to do our best. Okay, so we're going to kind of go through this and work it. Hopefully you have your code book handy that you can follow through with me, and we can go through this process, and it's going to be painless for you, especially if you're preparing for an exam. All right, so I got a house, and I'm just going to throw some numbers out there so that you can follow along. When people get a question on the exam, they panic. When you see it in real life, I've even had experts who I will say, guys, give me these values and give me an answer. And they stall and panic, and it really starts to... It's not that they don't know how to do it. It's just the concept of how it flows. Sometimes a code book can be very daunting. And when you see how things kind of jump around, it gets pretty confusing. And so we want to remove the confusion, okay? All right. So in this confusion, let's now get into the madness. Number one, when I'm looking at the actual application for a dwelling unit, for example, the first thing I want to look at and take into consideration in that dwelling unit is all the requirements. And so I'm looking at the outside dimensions of this unit, okay, this dwelling unit or this one family dwelling. Now remember, the standard method load calculation for one family dwelling is still the same process you're going to use to determine what the load is for an individual dwelling unit of a multifamily building. Okay, so there's the first place people get confused. They want to do a calculation for a multifamily dwelling, and they realize that they're sizing the service, in this case, or even possibly a feeder, based on the entire load of the building versus the individual units. Now, when you're doing the individual units, you need to use a standard or optional method. When you're doing the actual multifamily calculation, it's slightly different. And you can take into account all those units. But you're still going to use a lot of the information that you're going to gather by doing the calculation for each individual unit. So when we teach this, we teach the standard method for a one-family dwelling. And you know that can also apply to each individual unit of a two-family dwelling. Or it also can apply to the individual unit of a multifamily dwelling. That's why we teach you the standard method first. Okay, because you can use that. For example, if I was doing a feeder to an individual unit of a multifamily dwelling, I have to calculate the load for that individual unit. And that's what we're going to do here. We're going to use the standard method, okay, to do that first. Again, I could use the optional or standard for that, but we're going to use the standard method, okay? All right, so in this case, if we're talking about a dwelling unit, and it's a one-family dwelling, and we're going to give some dimensions, kind of give you some context to what we're talking about here so that you know where we're working from. It's a 35, let's see. I'm going to give you a different one. I'm going to keep it within the scope of what we're working on today. Let's see here. Bear with me. Let me see if I can find some values that I want to work with here. Bear with me. Again, I was a little unprepared for this, so I wrote them down, and now I gotta find what I'm doing here. Okay, good deal. All right, now so here we go. All right, so what we're going to do is we're going to do the calculation based on some variables for the loads that we have, and what we've got here is 2,500 square foot dwelling. So that is the outside dimensions. Okay. And we'll cover all these things here in a second, the different code rules. So that's the outside dimensions. We have a range. It's a 12 kW range. We have a water heater, which is a 4 kW water heater, which again, remember, when we see kW and we're doing this calculation, we need to remember that in this application, we're going to actually use the actual kW is synonymous with VA, okay? That's how we're working it. We have a dishwasher. It's 1.5, which converts to 1,500 VA. We have an in-sink waste disposer, which is a 3rd horsepower at 115 volts, but we know that we got to go. And up front, if you're doing an exam and you get these values that are horsepower values, like for your air conditioning units and your in-sink waste disposal, stop right there and immediately convert these into VA. Now, how do you do that? We want to talk about that first because you need to set the foundation before we can start doing things in step-by-step process. Right now, we're just looking at the values. Well, the first things first, if we're dealing with a 115-volt motor, and this was a waste disposal, and it's a 3rd horsepower, we're going to have to go to 430.248, and in that list, and I'll do this with you so we can go to that list, 430.248, what we're going to go to is the table, and you'll see that the 248 table is for full load currents for single phase alternating current. And you'll notice that when we deal with 1/3 horsepower, it is at 115 volts, it is 7.2 amperes. Okay? So when we got 7.2 amperes, for that value for the disposer. How do we convert that into VA? Because we're working with VA, okay? That's what we have to convert everything to. So we take that 7.2, we multiply it by 115 volts, because that's what the exam gave us, or the test gave us, the question gave us, or our calculation gave us. And that's what the motor's based on. And that ended up to be 828 VA. Okay, so when we're doing our analysis for the fastened in place appliances, the disposal is going to have a value of 282 VA. Okay, the next we have a clothes dryer, which is 4 kW, but we know that if you look at 220.54, it says that it has to be for a standard method for the dwelling unit, it has to be 5,000 or the nameplate, whichever is greater. Well, in this case, it was 4 kW clothes dryer, so we have to use 5,000. So in our calculation, we're going to use 5,000. Okay, no brainer there. The next, it says it has electric heat. It has 2 banks at 3 kW each. So the heat is 6 kW. And it's an air handler with electric heat, so it's 2 banks. So we will kind of go on the premise that this is a heat pump application. So that is 6 kW at 240 volts. And it has an air handler blower motor. Now this is something unique to remember. And I'm kind of just going over the values here with you. The blower motor for the air handler is going to work whether it's AC or heat. It doesn't matter. You still got to blow that air around your house, right? So when we're comparing the larger between the AC and the heat later on in our process, just remember that you're going to also incorporate the actual blower motor's value, because it's going to work in either the heat or the AC. It doesn't really matter. That is going to run. All right. And so generally, because these are non-coincidental loads, that means that they're not going to run at the same time. And so what happens is when the heat's on, the AC won't be. If the AC's on, the heat won't be in general. But when you're dealing with a heat pump, you have to take into account the potential for the heat to also run when the compressor is running. So you have to take those things into consideration, okay? Don't worry, we'll do all the calculations on our example later as we're looking for what all we're working with, okay? All right. The next thing we're looking at is the air conditioner compressor, and that is 5 horsepower at 230 volts. Well, the first thing that we want to do, we have to step back. The air handler. That was a 4th horsepower at 115. So we go back to that 430.245, and we see that 1/4 of horsepower is 5.8 at 115 volts. So again, we got to convert that. We need to convert that into VA. So that's an easy process. You just get your calculator out, and you found out that is 5.8. So it's 5.8 times 115, and that is 667. So you write that down. So that is your VA for the actual air handler blower motor. Now you're going to use that 667 both with the heat or the AC, depending on which one you choose, because again, it works for both of them. The next thing we have is the air conditioner compressor, and that is a 5 horsepower at 230. So again, you go back to that table 430.248 because that is a motor, and it's treated as such. Okay, the compressor has the motor, and you use the same values of 430.248 in order to come up with that value. And so in this situation, since it is horsepower, that kind of should lend yourself to that. Then you go here and you see 5 horsepower at 230 volts is 28 amperes. Okay, so that is 28 amperes. You write that down. So that's 28. Now the last one is the condenser fan motor that's inside of that outside air conditioning unit. And that is 1/6 of a horsepower, okay, at 115. So you'll look here and you see, again, you're at table 430.248, and you see 1/6 at 115 volts results in 4.4 amperes. Okay, so again, you're going to convert that to VA. So it's 4.4 times 115, and that is 506. Okay, so you write that down. So those are your three. You have converted all of your horsepowers into VA. That's the first thing that I recommend you do if you happen to have this on an exam or in real life. Convert all of your motors and air conditioning, everything into an actual VA value, because that's what you're working with, VA. Okay? Now remember, the clothes dryer might say it might be 5 kW, but in reality, you're converting that. That K is 1,000, and so watts is synonymous with VA in this calculation. So, and it also says that under 220.54 and 55, whether you're dealing with the dryer or ranges, that means the same thing. So that 5,000 kW, or that 5 kW is actually 5,000 VA. Okay? All right, so we've got all our values here, remembering that the water heater, clothes dryer, ranges, electric heat, the kW is actually equivalent to a kVA, and ultimately you're breaking that down into the actual VA, okay? For example, 5 kVA is 5,000 VA, okay? All right, we understand that. We feel good about what we're doing. So let's move forward. So that's the first step. Before I even get into a calculation, I've got to break down all of these. So if you're doing an exam or you're in the real world, just relax. Relax and go, okay, I'm breaking this all down. I've got to show, otherwise I got to determine these horsepower. I got to get a VA value. I can't work in this horsepower they give me. I got to break it down and come up with a VA, and that's how you do it. All right, so now let's get to this process. All right, first things first. We're looking at this dwelling, whether it's a dwelling or dwelling unit. We're looking at it, and we have to go by the outside dimensions. The first thing we look at in the National Electrical Code is, in the first step that we're going to deal with, is to determine the general lighting and receptacle loads that we're working with. And that's going to take us to section 220.12. So that's where we want to be. So you're going to go to 220.12. And in there, you see that 220.12, which I would highlight that if you can highlight in your code book. Again, you need to make sure in your state that you can do that. It says the lighting loads for specific occupancies. Okay? So 220.12 is telling us that a unit load is not less than specified in table 220.12 for occupancy specified shall constitute the minimum lighting load. It says the floor area of each floor shall be calculated from the outside dimensions of the building. Now, on an exam, they might just give you dimensions, and you can work with that. In the real world, you want to measure from the outside dimensions, okay? So it's from the outside dimensions of the building, dwelling unit itself, or other areas involved. It also goes on to remind us that for dwelling units, again, this applies to dwelling units, it says the calculated floor area shall not include open porches, garages, or unused or unfinished spaces not adaptable for future use. Okay? So in our scenario is that we don't include the open porches, we don't include garages, we don't use the unused or unfinished spaces not adaptable for future use. Okay? So a question on an exam is going to have to tell you whether a space is adaptable or not, or unadaptable. So you assume it is if they don't tell you otherwise. But let me give you an example of a place that's not adaptable. Is a attic space that is not adequate due to whether it's the floor trusses sizing or the head clearance, or all those things would be spaces that would be not adaptable for future use. Okay, but a basement, for example, even if it was unfinished, it is still adaptable for future use, so I have to count that floor area. If you can determine that it is not adaptable, then you don't have to do that, okay? You're going to have to talk with your local jurisdiction on that, but using a little common sense, we can come up with what it is, whether it's considered adaptable or not adaptable for future use, okay? So we're going to assume today that our value for the use is 2,500 square feet, okay? So our length times our width is giving us 2,500 square feet. That is our value. Now, first things first, we're going to go to 220.12, the table. So you'll go down to that. In that table, if you're in the hardbound version, then it's on page 71. If you're in the PDF version, it's on 74. Kind of just following along. And you'll see a table here. The table says 220.12, general lighting and load by occupancy. Now, if you come down that list on the left, it tells you the different types of occupancies, and you have a bunch of different ones. But what we're working with today is dwelling units. Now, you'll see dwelling units, and it's down, a couple down, and it says it has a little A as a footnote beside dwelling units. Okay, let's talk about this in the full scope of what we're working with. Because a lot of people get lost in this because it says general lighting loads, and they think, well, don't I have to do something for receptacle loads? And the answer is yes, and that's what that little footnote is. It's 3 VA per square foot for dwelling unit. Okay, so in our case, it was 2,500 square feet, but that's going to be times 3 VA, because the VA, the volt amps in square foot, is what's going to give us the actual loading values that we need for the dwelling unit to cover our general lighting. But that little A sends us to the bottom of that table. And you'll notice that A says C220.14J. Well, if you look at 220.14J, that's basically going to say, hey, guys, any of those general use receptacles that are 20 amps or less, all of those spacing requirements that we do in 210.52 and all that kind of stuff, all of that's going to be included in it, all right? Even the receptacles for the bathroom, don't worry about it. Don't have to add anything additional to that. It's all included in there. Now, of course, that's not going to include the small appliance in the laundry, which we'll calculate here in a minute, but that's all of the other general use stuff. Not any dedicated circuits that's not considered general use. I'm just talking general use, okay? It also says any of the receptacles that are specified in 210.52E or G, and we're talking about things like the basement applications and garages and whatnot like that. Don't worry about it. It's already figured in. You don't need to figure anything for that application. It's already assumed as far as doing the load calculation. Don't stress it out, okay? So that's what's going to cover the receptacles, all right? So rather than 220.12 actually saying that, saying general lighting loads by occupancy, it uses the footnote to direct you to where it incorporates the receptacles when it comes to dwelling units. Now, if you're doing commercial calculations, then that's not going to apply because we have other values under I, for example. That's I as in Indiana, I. In that application, in 220.14i, that's going to talk about the receptacles for things like commercial buildings where it's 180 VA per strap and whatnot. Or if you have 4 or more receptacles, it's calculated not less than 90 VA per receptacle. Look, that's commercial. We're in dwelling units. I have a lot of people that'll ask me, when I say to them, how many receptacles can you have on a circuit? And they'll say, oh no, it's 180 VA per strap. And I'm like, get your mind out of commercial. You're in dwellings. Nothing in the code says how many receptacles I can put on a branch circuit other than common sense and whatever the load might be. Okay? The lighting load is a given because of the watts and whatever the load is based on the light you're putting in. But receptacles, there is no value. I could put 100 of them on a circuit if I want. Now, there is a calculation to determine how many branch circuits we need, and we're going to talk about that when we get to our basic calculation segment of our podcast, which is not this one, that's another one, and I teach you all those easy formulas for determining that. That's a different thing, okay? Just remember, we're dealing with the dwelling unit, and we're dealing with all of the general use receptacles, which get incorporated into this calculation that you're going to do under table 220.12, okay? It all gets incorporated in that 3 VA per square foot, so you don't have to stress it out, okay? All right. Now, you're going to use common sense when you're laying out your branch circuits. So we're talking at a 50,000-foot view. You want to limit, obviously, the number of receptacles on a branch circuit using common sense. But I'm just using that as a metaphor. It's not a certain VA per receptacle when you're dealing with dwelling units. Okay? All right. So we're now in the dwelling unit, and it's 3 VA per square foot. And, of course, the general use receptacles are all incorporated in here. So the first thing we want to do is try to determine our general lighting and receptacle loads based on 220.12 in the associated table. And so we know that it's 3 VA per square foot. So we'll do 3 times, and what was our square foot? It was 2,500. So it's 3 times 2,500 equals 7,500 VA. So you would write that down. That's number one. That's the first value that you're going to write down. Okay? The next thing we want to do in the code is, okay, we got our general lighting taken care of. We have our receptacles for general use taken care of. All those receptacles that we would place every 6 and 12 feet and around in through the rooms and everything. We're good there. Whew, we got that taken care of. Next thing we want to deal with is the small appliance branch circuits, and that's under 220.52a. So now we're going to jump down into part 3 when we're doing the calculation. Now part 3 is going to jump us again into 220.52a. Now if you look at 220.52a, it says small appliance circuit load. It says each dwelling unit, the load shall be, it's in each dwelling unit, the load shall be calculated at 1500 volt amperes for each 2-hour small appliance branch circuit as covered by 210.11c1. Now 210.11c1 says you have to have at least 2. Okay? If you have more than that, you have to account for them. If I have a really big house where I have 5 small appliance branch circuit, then it's going to be 150 VA per small appliance branch circuit. In our example today, we're just going to do the minimum that code requires, and that is a minimum of 2. So I've got 2 small appliance branch circuits. Now, each one of those have to count for 1500 VA. So we go 1500 VA times 2, and that is 3000. So that's the next value you write down, because we're going to add that 7500 to this 3000. Okay? Now, small appliance is taken care of. We don't do anything else for that. Now, we move on to the next step, and that is dealing with the laundry branch circuit. And that is 220.52b. Remember, we're already here doing the small, so we might as well cover the laundry circuit load while we're here. Now, laundry circuit load for a one-family dwelling. It says a load is not less than 1500 VA, just like we did for the small appliance, shall be included with each 2-hour laundry branch circuit installed as covered in 210.11c2. Now, 210.11c2 tells you that you're going to have at least one laundry circuit. Okay? Now, I can have multiple receptacles, for example, on this laundry circuit if they're to facilitate laundry needs, like a ironing board or whatever in the laundry room, for example. Okay? So, but even the washing machine, for example, is figured in to this laundry circuit, okay? And this is a 20 ampere laundry circuit, and that is what's required by 210.11c2, that it be a 20 ampere laundry circuit. And incidentally, if I had 2 laundry circuits or 3 laundry circuits, branch circuits run, then I would count 1500 VA for each one of those. In our example, we only have the minimum of 1, so we're only going to put 1. So that is 1500 VA. So now I've got 3 values. I got 7500 for our general lighting and receptacles. Okay, again, remember, we're just walking through this as we're doing the calculation. Don't make it difficult. I've got a 7500 for that. I've got 3000 for the 2 small appliances. That was 1500 times 2. And then I've got 1500 times 1 for the laundry, so that's 1500. So that's 7500 plus 3000 plus 1500 for a total of 12,000 VA. Okay? That's where we're at so far. Now, what do I do with this 12,000? Well, the beautiful thing is now nobody's going to use all those receptacles and the loads at the same time, so we're allowed to apply some demand factors here. We know that there's diversification involved. So, next table you're going to want to go to is table 220.42. Now, when you see 220.42, it says lighting load demand factors. Now, of course, we know that it is also incorporating what? Receptacle loads in there and the lighting. We already know this, okay? So, don't worry about it, okay? It's just a given, okay? Following the code, we know that that's what it's allowing us to do. So, in our case, we started with the 12,000. Now, what does it say for dwelling units? It says the first 3,000, you take it at 100%. So the easiest way that I do this is take my total load, which is 12,000, and I actually take the 3,000 away from that, because I want to work with the remainder part, because I know that the first 3,000 is 100. It's going to be 3,000. So I take that 3,000 and I set it aside. I write it down, 3,000, right over here. That's going to leave me with 9,000, which is 12,000 minus the 3. What do I do with that 9,000? Right? Well, that 9,000 falls into that range of 3,001 to 120,000. So it falls in that category. So here, I'm going to apply the demand factor in percentages of 35% for that value, that remaining 9,000. Okay? So when I do that, I take the 9,000 times 35%. And that's going to give me 3,150 VA. What's that do next? Well, remember that 3,000 that I set aside? I'm going to add it back in now because I was 100%. So now I add the 3,000 back to it, and that gives me 6,150. Okay? Now, write that number down. That's your very first hard value that you're going to have to add up at the end. So you write 6,150. Now, if you're on an exam, if they ask you the total general lighting and receptacle load on an exam, remember, it's asking you for that general lighting and receptacle. It's assuming that you do the small appliance. It's assuming that you do the laundry, unless it states otherwise. This is a cumulative value after you've applied what? The demand factor. Okay? So, that's what we've got. And that is, the total value is 6,150. So, that is my total general lighting and receptacle load. Okay? So, you've written that down. Pretty easy so far. Well, let's move on to the next one. So now we're looking at our equation. Now remember earlier when I told you the appliances? Because that's what we're going to do next. We're going to move to 220.53. It just, chronologically, it just works that way. So you move down to the next one. And we're going to talk about the appliances. Let's knock those out. Now in our equation, we had a water heater. And that was 4,000 VA. And we had to get there because it said 4 kW. So we know that that is synonymous. The K represents 1,000. So it's 4,000 VA. And remember, we want to convert everything into the VA. And so we have that. Also, we had a dishwasher. Now, that dishwasher was 1.5 kW. We know that we need to convert that into VA. So since there's a kW, we know that watts and VA are equivalent when we're doing this work. So 1.5 results in 1,500, okay, VA. And so we write that down. So I've got a 4,000 and I got a 1,500. And then the only other appliance we had here was the in-sink waste disposer. And remember earlier while we did that conversion so that we didn't have to do it now, it was 1/3 horsepower at 115 volts. We're going to do that value. And when we did that conversion, it resulted in 828 VA. Remember we did that earlier. Okay, we had to go to 430.248, find the horsepower, take that voltage, take that amperage and multiply it by the voltage in order to come up with the VA. And we did that, and we came up with 828. So that's why it's better for you to go on and knock those out the way up front. Get that stuff so you've got nothing but good numbers to work with. Okay, there's a less chance that you'll forget something if you do that. All right, so now we write that down. So we've got three values. We've got the 4,000 for the water heater, the 1,500 for the dishwasher, and the disposer, which is 828. We add those three together, and that's going to result in 6,328. Now, one thing I want to bring your attention to. This 220.53 says that it shall be permissible to apply a demand factor of 75% to the nameplate values, which is what we just did, when you've got 4 more appliances that are fastened in place. And we're not including things like the electric range, clothes dryer, space heating equipment, or air conditioning equipment, okay? We have a different calculation for those things. We're just dealing with the other items, the other appliances that are fastened in place. Now, a water heater is covered under Article 422. That's appliances, so we obviously know that is, and it's fastened in place. You ain't going to be moving that around. Same with the dishwasher. It's connected to the counter. It's fastened in place. Disposer is connected to the sink. It's fastened in place. Those things are very much part of this fastened in place appliance that's covered under 220.53. Now, we took those at the full value, but if there had been 4 more of them, then we would have applied a 75% to that. Don't forget that if you're on an exam. In our case, it was only 3, so we're taking them at full value. Okay, we don't get any demand factor for that. All right, so that was our next number we wrote down, a hardcore number, and that is 6,328. So you've got 2 numbers you wrote down. 6150, which is your general lighting and receptacle loads, and now we wrote down our fastened in place appliance loads under 220.53, and that was 6,328. That's 2 values we want to write down. See how this is working out? What's next? Simply follow down the list. Next, we're going to electric clothes dryers. All right, again, one family dwelling or individual dwelling units of a multifamily building can use this process. It doesn't change. All right, so we're dealing with the clothes dryer. for that individual unit. Now, what does the code say about clothes dryers? It says the load for a household electric clothes dryers in a dwelling unit shall be either 5,000 watts, and of course we can say it's VA, and it tells us that actually in this section, or we use the nameplate rating in whichever is larger. Well, in our case, our clothes dryer was 4 kW. But since we're using the standard method, and 220.54 falls under Part 3, which is the standard method, and we're doing an individual dwelling unit or a one-family dwelling, then we're going to use 5,000 because that is larger than the 4,000 that is the actual one that's in the actual unit. So we take the 5,000. So the next hard value that you write on your piece of paper is 5,000. Just that simple. You write it down. That's your next hardcore number. So you've got 3 numbers now written on paper. Let's go on to the next one. The next one says, and again, we're following down the list. We're simply going down now to 220.55. We're going to deal with the cooking. And in our case, we had what? We had a range at 12 kW. Okay. Well, the range, oven, cooktops, and other household cooking appliances over 1750 watts in 220.55. In our case, we had a 12 kW. So if we go look at table 220.55, then we're going to notice that since our range falls under column C, and of course the table's heading reminds us that you're going to use C in all cases except where permitted in note 3. Now, note 3 is talking about when the actual cooking equipment or appliances fall between 1 3/4 kW through 8 3/4. Well, our case, it doesn't. It falls squarely in column C. If you want to know how to do the different size ranges and all, go watch my video on range calculations, and you'll get all the understandings that you'll ever want to know on how to use column A, column B, column C. In our equation, it's very simple. It falls under column C. And since it's not over 12, we go to the number of appliances, which is 1, and then we go to the right and we see that we get to use 8 kW. Now, if you're doing an optional method, you can simply take the value that the nameplate is, and it would have been 12 kW, and that makes an easier calculation. But in the standard, we're using part 3. We're going to go to column C, and you see that we can use 8 kW. We don't have to use 12 kW. Okay, that's the demand factor that we're allowed. The maximum demand in kW, which is synonymous again with VA. So 8 kW is 8,000 VA. And guess what? That's the next number we put on our piece of paper. It's 8,000 for that 12 kW range. All right, we're moving along pretty good now. All right, the next one we want to talk about is let me go back to where I was. The next one we're talking about is we do a little bit of a jump, and we're going to jump to the heating and air conditioning, and that's where you see 220.60. Now, 220.60 says non-coincident loads. Non-coincident loads that are loads that are unlikely that 2 or more non-coincident loads will be used simultaneously. It shall be permitted to use only the largest loads that will be used at one time for calculating the total load for a feeder or service. Okay, so in our case here, we're going to either determine whether the heat or the air conditioning is being used. And we have to compare the two, okay? That's what we're going to work with now. We're going to try to determine which one of those based on our example. And we're going to relook again at what we have in our equation. Now, let's cover that real quick. So, heating. Our electric heat says that we have 2 banks of 3 kW each. So that's 6 kW at 240 volts. That's our heat. That's our electric heat. So that's 6,000 VA. We know what that is. Now, we have a blower motor, which is under our air handler. Now, that blower motor, we've already calculated, remember earlier, what the VA was on that. That's going to apply to the heat as well as the air conditioning. Because why? It doesn't matter. If I have an air handler, it's still got to blow this heat. Okay, it still has to blow it around the building. So that load on that motor is going to be used either or, whether we select the heat or whether we select the actual air conditioning. Okay, just remember that. Don't let that throw you. We're going to select. Okay, that is also going to be included regardless of which one we pick. Okay? All right. So we already did our math earlier. We knew what our values were when we're dealing with our air handler, our air conditioner, and our condenser fan motor, right? We've already solved those. And those values are, let's see, remember the 1/4 horsepower at 115 volts for the air handler was 667 VA. The air conditioner compressor was a 5 horsepower at 230 volts. We looked that up at 430.248, and that is, the value was 28 amps times 230 volts. Again, use what's on your exam question, okay? And so in that case, it was 6,440 VA. And then the condenser fan motor was 1/6 horsepower at 115 volts. Okay, so we did that math, and what we've got there is 506 VA. Now, look, at this point, it probably doesn't take a brain surgeon to look and say, look, if the heat is 6,000 and all you add is the blower motor, and that only adds another 667, that if the air conditioning compressor is already 6,440, plus the fact that I got to add the condensing fan and the blower to it anyway, then the air conditioning is going to be the greater of the two, right? Makes sense? Right. So we're going to use the air conditioning and we're going to omit the heat. So in that case, I simply add up. That's the next step. So in step where you do the heat versus AC, since we're using the AC, you're going to add the air handler motor at 667 VA, the air conditioner compressor at 6,440, plus the condenser fan motor at 506 for a total of 7,613. Well, guess what? That's the next hard number that you write down. So by this time, you should have 6,150 for the general lighting and receptacle. You should have the fasten in place should be 6,328. You should have the clothes dryer written down. That's 5,000. You should have the range written down. That is 8,000. And now you should have the air conditioning value because that was larger than the heat, and that was 7,613. That's our next one to write down. Move on to the next step. And the next step is actually the last step of formulating by going and gathering. Okay, when we say gathering. All right, so now we're back, and you're going to be at the value you're going to see is 220.50. So this is your next one. So 220.50 is going to tell us for motors. It says motor loads shall be calculated in accordance with 430.24, 430.25, and 430.26, and with 440.6 for a pneumatic refrigerant motor compressor. So that tells us we have to account for the motor itself. Okay? So what that means is we're taking the full value of the largest motor or pneumatic refrigerant motor compressor. Okay, that's what we're dealing with, motor compressor. And we're adding that additional 25% because we're supposed to take those at 125%. So we've already got them at 100% because we went and looked at their ampacity values from the back of the book. So now we're just simply going to gather the additional 25% that's necessary. So in our case, since we're using the AC was our largest load, and we're not using heat, so we're only looking at our AC, then the next logical one would be that air conditioner compressor, because that one was 6,440. Okay, well, if you didn't have it, and let's say you were using the heat, then you would look at possibly the blower motor's value for that motor, or you might even have to look at the actual waste disposer. Whichever is the largest, that would be the motor that you use, okay? But in our case, since we use the AC, because that was the largest, then that's when the largest motor comes into play for us would be the air compressor motor, okay? So that's how we got the 6,440. Now, we do that, we multiply that by 25%, because you remember we already accounted for the air compressor when we did the valuation before in the heat versus AC. So all we need is that additional 25%. So we take that 6,440 times 25%, and that equals 1,610. That's the very next hard number and our last hard number that you're going to write down. And so you write down 1,610. Now, you add all of these up. Now, when you add them all up, you'll get 34,701. That is your total volt ampere demand load. Okay, so if that's a question on your exam, that is your total VA demand load for this one family dwelling. It's 34,701. So let's recap. Okay, the general lighting and load was 6150. The fixed appliances was 6328. The clothes dryer was 5,000. The range was 8,000. The heat versus AC resulted in the AC. That was 7,613. Of the largest motor in the set that we're including in this calculation, it was the air conditioning compressor at 6,440 times 25%. That gave us 1,610 when we did the largest motor. And again, the air conditioning was 7,613. So we add those all up, and that's how we got the 34,701. Now, in order to find out what our minimum ampacity is for our ungrounded conductors, we would do 34,701, okay, and we divide that by 240 volts. That's what our 122 40-volt load is. That's what our question was based on. That results in 145 amperes. Well, we're going to find a breaker that accommodates the 145, and if we go to 240.6a, we'll notice that it doesn't, but there is a 150, so I'm allowed to go to the 150, okay? Now, I have to have a conductor that can at least handle the 145 amperes, okay? But our overcurrent device is going to be 150 amperes, okay? Now, couple things we want to think about, especially when you're working an exam, okay? And what are we talking about? Now we're going to kind of do a little bit of a shifting gear. We want to talk about the application of, because right now we know what our circuit, our breaker is. It's got to be a 150. We got that. We're really good. Now we're focusing on conductors, how to size the conductors. Now, I could go to 310-15B16 and simply go to 75-degree column, because that's probably, I didn't say anything about adjustment of corrections here, anything like that. I could just go to column, to the 75-degree column. If I tell you that they're THHN or THWN or whatever, but because of terminal limitations in 110.14c, and if you don't know what that is, you need to go watch our derating demystified video, and that'll explain all conductor sizing. And everything that I'm going to talk about here generally. But we've determined we need 150 amp rating for the service, a service rating. Okay. Now, what is the minimum size conductors we need here? Now, if you want to go to 310-15B16 and just pick one from that table, you can do that. I mean, there's nothing that says in the real world that you can't do that. Okay? You're going to be fine. But this is an exam. And on an exam, you need to be the best option. And so there is a minimum conductor size that you have to adhere to. So if I were to just go to 310-15B16 and say, okay, give me one that can handle it, all right, then I'm going to be at a 1/0, okay, for copper under 75. I'm going to be at a 1/0, okay? All right, well, let's see how this works, because maybe I don't want to run a 1/0. What is the minimum? So I'm going to direct your attention to 310-15B7. Remember, this service is only 150. So let's go and see what that says. All right, so if you go to 310-15B7, it says single phase dwelling services and feeders. In a one-family dwelling and individual dwelling units of a two-family and multi-family dwelling, service and feeders, conductors supplied by a single-phase 122 40-volt system is what we're working with here, okay? Then we're going to be able to use this little table. Now, years ago, it was a mini table. Now it's in Informative Annex D in the back of the book. The table's still there now, but it's no longer here, because here we're going to make you do a calculation. And look, it's not a difficult calculation, but we're going to make you do it. So if your exam wants to know what the minimum size conductor is, well, what we did earlier would not be the minimum size. 1/0 would not be the minimum size, because this rule does apply based on the information that I have given to you. I've told you it's a 122 40-volt 3-wire single-phase one-family dwelling. Well, that meets this rule. Now, if you go down here and you look at option number 1, it says for services rated 100 through 400 amperes, and that's what we've got here. We've got one, it's rated 150, so we firmly fall here. It says the service conductors supplying the entire load associated with a one-family dwelling, and ours does, or the service conductor supplying the entire load associated with an individual dwelling unit in a two-family or multi-family dwelling, shall be permitted to have an ampacity not less than 83% of the service rating. Well, our service rating was 150. So it can't be less than the service rating. So if I were to take this 150, okay, and I do this times 83%, then I'm going to get a value, okay? And that value is going to be 124.5. So now I take that value and I go back to 310.15b16 and look and see, well, now, what do I need to accommodate that? So when you do that, all of a sudden now you go under 75 degrees C, because again, we're not applying any adjustment or corrections. If you want to do that, go watch my Derating Demystified. I'm just trying to show you the basics here. You'll see that a 1 gauge is good for 130 amperes. So a 1 gauge at 75 degrees C is good for 130 amperes. Okay, so that is at least, and so it can't be any less than 83%. So this would allow me, due to diversification, to in this little mini table, if you will, it used to be here, now it's in the back of the book, based on a calculation, I can be a 1 gauge copper, and I can be okay. All right, now, subsequently, if I was doing that with aluminum, then it would be a value, the same scenario would apply. I have to have at least 100, so that would be a 2-aught aluminum, okay? But that's how it works, okay? So you can apply 310.15b7 for this service. Now, what is the feeder that's going out to the dwelling unit? Okay, well, that feeder, if that dwelling unit in that panel in there is supplying 100% of the load on that dwelling unit, then that allows me to use the allowance here in 310.15b7 option number 2. And that's dealing with the feeders, okay? All right, so same rules apply. It's all based on that feeders rating. You do the same rule. That's how it applies, okay? Now, at the end of the day, I usually like to round this out and ask people will say, okay, Paul, well, now you need to show me how to size the grounding electrode conductor to the ground rods. Well, if it's a ground rod, then you just go to 250.66a, and it says it doesn't have to be larger than a 6 copper or 4 aluminum. Okay, so since it's a ground rod, you're probably not going to run 4 aluminum because that termination is going to be less than 18 inches from the earth, so you're probably going to use copper. So you're going to run copper, so it doesn't have to be larger than a 6. Now, if it's a water pipe, or if it's a structural steel, for example, I'm just using that in general terms, then you're going to pull the values based on the size of the actual service conductors. You're going to pull that size based on 250.66. But you do have the allowances in 250.66 A, B, and C, whether you're dealing with a concrete encased electrode, a ring electrode, or a pipe, plate, or rod, which is going to give you some allowances to be some sizes given under those tables. If they're not those items, then you're going to use the values in the table 250.66 based on whatever the size of the service conductors are. And that's how you're going to size your grounding electrode conductor. Hopefully you got that. Okay. Now, last thing I want to do is round this out by saying, okay, Paul, you've talked to us a lot about that. What size does a neutral have to be? All right, well, now I'm going to show you how to size a neutral under the standard method. Now, another thing to remember, whenever you're sizing a neutral, it doesn't matter whether you're using the optional method or the standard method. To size your neutral, you're going to have to use the you're going to have to use the standard method, okay? You're going to have to. There's no ways around it, okay? So now, here's the beauty of doing the neutral. Really, it's just this simple. All you care about is all of the loads that are going to have 115 or 120 volt, whatever. In our case, all of them are given in 115. So all of the circuits that are going to be the 115, or when you're dealing with general lighting or receptacle, all the things that are going to be a 120 branch circuit. That's what you're worried about. So, really easy. The first steps that we did for the standard are exactly the same for the neutral because those are purely loads that are going to be used and want to be on neutral. They are current carrying conductors. They are circuits. That means that you're going to have current going out, current coming back, so you have to account for those for that neutral. So they are an actual given load. So when I'm sizing the neutral, I got to have the general lighting receptacle load. Nothing changes. So all I got to do is transfer the loads that I had before. In fact, you could actually take the whole part of the top of that standard method that gave us the 6,150, start with that value. Because that's what you're doing. You take 100% of the general lighting and receptacle load, because all of those loads are going to be 120 volt neutral loads. Okay? So you simply take that value. So that's the first value you'd write down. Now, the next step for the neutral is, what about those fasten in place appliances? You're following the same logical order. How many of those have 115 volt loads on them? Well, the water heater didn't. That was a 230 volt. Okay? And realistically, it was a 240 volt. So what about the dishwasher? Well, the dishwasher was a 120. And what about the disposer? Well, the disposer was a 115 because there was a motor involved, and that's what we're going to use that table in the back. So at the end of the day, yes, it is a neutral load. So I have to account for both of those. So the 1500 for the dishwasher gets written down, and the 828 for the disposer gets written down. You can take those values directly from the last calculation you did. All you got to do is leave off the water heater. So I add those two together, and that is 2,328. Now, again, it's not 4 or more appliances, so I don't get to apply any percentage. It's just take them at face value. If I did have 4 or more, then I could even apply 75% again. Okay? All right. Next thing, we're just going down the list. So I write that down. So I should have 6150, and now I got 2328. So the very next thing, again, same order as we did before. It's just that simple. Is the clothes dryer. Well, we knew the clothes dryer was 5,000 VA. However, we do have an allowance for the neutral demand when it comes to 220.61b of the National Electrical Code. All right, now, in 220.61b, it says very specifically that I can take it as 70% permitted reduction. Okay? So in that permitted reduction, I'm going to take that value for that clothes dryer, okay, and which was 5,000, and I'm going to multiply that by 70% or 0.70, whatever your flavor is of your calculator. And that comes out to 3,500 VA. So that's the next value. Basically, that's 70% of the 5,000 VA. So you write that down. So that's your next value you write on paper. The next one is my range. Well, the range was 8,000 under our standard calculation, but again, under 220.61b, it says that I can take it at 70%. So I take that 8,000 and I multiply it by 0.70 or 70%, whatever your calculator likes, and that's going to give me 5,600 VA. So you guessed it, I write that down. That's the next hard value that I write down. The next one is the heating and air conditioning. Well, obviously we chose the air conditioning. That was our largest, okay? And all we're concerned about here is our neutral loads. So I'm going to add the 667, which was for our blower motor, and I'm going to add it to the 506. And that's where we get the 1,173. That's the only neutral loads we have. The air conditioning compressor is a 230 volt load. So what's my next hard value that I write down? 1,173. So I'm adding these up. And what's next? Remember, we still have to worry about that largest motor. Well, the good news is, in this scenario, we're looking at what is our largest motor in our equation here. Now, here's where it can trick people, okay? We have to take the largest motor in the set. Now, you might think that since we're doing a neutral, and we have the air handler and we have the condenser fan motor, but what about that in-sync waste disposal? Remember, the air handler was only 1/4 horsepower. The condenser fan was even less. That was a 6 horsepower. But guess what? That waste disposer was 1/3 horsepower. So that is the largest motor when it comes to the neutrals that we're involved with. Okay? So what do we do here? All right. So in that scenario, we added that value, and that was the 828 VA. Okay? So we took that value. Now, remember back when we did the standard method, whether I did that or misspoke that. In our case, on that one, we used the air compressor because that was the largest. But when we're doing the neutral, we have to look at all motors, and we got to think outside of the AC. So no, I was right on that. You all probably got it. But in this case, when we're doing the neutrals, we don't use the air conditioning compressor. We look at all of the other neutral loads and find the largest motor. Well, that waste disposer was the largest motor at 1/3 horsepower. So that's the one we're going to use. So we take the 828 and we multiply that by 25%. and that is 207 VA. So that's our last hard number. So what you should have is 6150 for your general lighting and receptacle loads, because they do all associate a neutral. We have the fasten in place appliances. We only had 2 appliances that utilize a neutral. That was the dishwasher and the disposal. Okay, so that was 2328. Next, we had the dryer, which was 5,000 at 70%. That was 3,500. We had the range, which was 8,000, and we did that at 70%, and that is 5,600. We did the heating and air conditioning, and obviously we used the air conditioning in our original standard calculation, so that's the one we're going to use. And in that case, it was using the air handler blower at 667 plus the condenser fan motor at 506 VA. We did the math, and that was 1,173 VA. So that's what we're putting there. Then lastly, we needed to find the largest motor that's going to handle a neutral load. In our case here, the in-sink waste disposer is the actual largest motor, and that was at 828 VA. So we do that at 25%, so we can gather that additional 25% for the motor, and that is 207 VA. Add those all up, and that is 18,958. Okay? Now, you take that 18,958, and just like you did before, you divide that by 240, and that's going to give you 79 amperes. That is what your neutral is. Now, a couple things to remember. Your conductor cannot be smaller, okay, than what's given for the neutral grounded conductor in what's called 250.102C1, okay? So it can't be smaller than that. So for what we're doing, so let's do that. I want to look at it, and then we'll go look at sizing and everything next. But we're going to look at that first. So we're at 79 amperes. So the first thing I'm going to do is compare it to 250.102C1, because that's what the code says for grounded conductors. So I got 250, and I'm going to do it with you. And I'm going to go to 250.102C1 and see what it says. I went too far. Sorry about that. All right, 102C1, and I'm dealing with the conductors, and we already know the conductors that are supplying this. All right, we already know what it is we're dealing with it. Okay? So in our case, it can't be smaller than. So what we're dealing with is the service conductor was a 1 gauge copper. Well, based on this, a 1 gauge copper shows that I'd need a 6. Okay, all right, so we're starting there. We're saying, well, I need a 6 copper. But is that going to be what we need? Well, now we have to look. That says it can't be smaller than that, but it could be larger than that. So now we're going to look at 31015B16 and select a conductor. So let's go to that. And so I'll go on and go to my code book, and I'm going to go under 75 degrees C, and I'm looking and saying, well, I need 79 amperes. And I never use the 90-degree column except for adjustment and corrections, and I know that most terminals are going to be limited to 75 or 60. If they're not marked, you need to be real familiar with 110.14C, which talks about terminal limitations, okay? And in this case, a 4 is 85 amps, whereas a 6 only good for 65 amps. Obviously, that's not going to handle our 79 amperes, okay? So, which one do we go with? Well, we have to go with the conductor that can handle the actual load that we calculate. In this case, that bumps us up into a 4 gauge. So the answer to the question is our neutral cannot be any smaller than a 4 copper. So yes, I've got 1 gauge for the ungrounded, and I got a 4 gauge for the grounded. And those are our conductor sizes. Okay? All right, so really it's just that simple. I walked you through the entire process of how to do the standard method, how to look at all these different aspects of it, and then I walked you through how to do the neutral conductor. Now remember, when we go to doing the optional method, sizing the neutral doesn't change. So don't get lost in this. So remember, whether I'm doing a single family dwelling and I choose the standard method, that's the process that I'm going to follow. If I'm doing an individual dwelling unit of a multifamily complex, for example, then when I'm doing the individual unit, I can use the standard method or the optional method. When you're on an exam, I showed you how to do the standard method. In the next podcast, we'll talk about the optional method, and I'll show you how that is much easier. We're going to use the same variables that we used in this example for that one, and it's going to be much easier for you to understand how to do optionals. Again, till next time, folks, I want you to stay blessed, and again, check out that insurance group. I'll have their information down in the link. I'm impressed with them, and I think that I'm going to be giving them a lot more of my business, and I want you to give them a consideration. Tell them that Paul sent you. Till next time, folks, stay safe, and God bless.
Every day, the future's getting closer. Every day, the future's looking bright.